Our solar system does not simply end where the planets stop. Beyond Neptune, beyond the frozen debris of the Kuiper Belt, there exists a vast spherical shell of icy objects so enormous that it stretches 1.5 light-years from the Sun in every direction. It has never been directly photographed. No spacecraft has ever reached it. And yet astronomers are confident it is there, surrounding our entire solar system like an invisible fortress of frozen ancient material. This structure is called the Oort Cloud. To understand why scientists believe in something they have never seen, we need to start with a question that puzzled astronomers for decades. Where do long-period comets come from? Most people are familiar with the idea of comets, those bright streaks of light that occasionally appear in the night sky as they swing close to the sun and release plumes of gas and dust. But not all comets behave the same way. Some comets follow short, predictable orbits. They return every few decades, sometimes every few years, completing lap after lap around the sun in a repeating cycle. Halley's Comet is perhaps the most famous of these, with an orbital period of roughly 76 years. These short-period comets are well understood. Astronomers trace them back to a region of space just beyond the orbit of Neptune, a broad band of icy debris called the Kuiper Belt. The Kuiper Belt extends from roughly 30 astronomical units from the Sun, where Neptune orbits, out to about 50 astronomical units in its main region, with a scattered outer extension that may reach as far as 1,000 astronomical units. When gravitational nudges from the outer planets disturb objects in this region, some of them get sent on new trajectories that bring them close to the Sun, and a short-period comet is born. 1 astronomical unit is the average distance between Earth and the Sun, approximately 150 million kilometers. So Neptune, at 30 astronomical units, is about 4.5 billion kilometers from the Sunday. These are already difficult numbers to hold in your head, but they are about to get considerably larger. Long-period comets are a different matter entirely. These are comets with orbital periods that can range from a few hundred years to millions of years. Some take as long as 30 million years to complete a single orbit. They do not arrive on predictable schedules. They come from all directions, not just from the plane of the solar system where the planets orbit. Their trajectories have no obvious pattern. They appear from above the solar system, from below it, from every angle imaginable. In the mid-20th century, this was a genuine scientific puzzle. A Dutch astronomer named Jan Oort decided to tackle it systematically. Oort was one of the most accomplished astronomers of his era. In 1927, he calculated our position within the Milky Way galaxy, demonstrating that our solar system sits far from the galactic center in one of its spiral arms. In 1932, he became one of the first scientists to find evidence suggesting the existence of dark matter. These were not minor contributions. Oort was the kind of scientist who solved problems that others had barely begun to formulate. In 1950, Oort turned his attention to long-period comets. He gathered data on their orbital characteristics and began looking for patterns. What he found was striking. Despite arriving from all different directions and having vastly different orbital periods, these comets shared a common feature. The point in each comet's orbit where it reached its greatest distance from the Sun, a point called the aphelion, consistently clustered around a specific distance. That distance was approximately 50,000 astronomical units from the Sunday. To put that number in perspective, Neptune orbits at 30 astronomical units. The inner edge of the main Kuiper Belt sits around 30 astronomical units, and even its extended scattered disk reaches only to about 1,000 astronomical units. 50,000 astronomical units is not just far beyond the Kuiper Belt. It is more than 1,600 times farther from the Sun than Neptune. The fact that these aphelia clustered around a specific distance, rather than being spread randomly, told Oort something important. These comets were not wandering in from interstellar space at random. They had a home, and that home was at a very specific distance from the Sunday. At the same time, they clearly were not coming from the inner solar system or the Kuiper Belt either. Their aphelia were far too distant for that. Oort proposed a solution. He theorized that surrounding our solar system, at distances ranging from a few thousand to 100,000 astronomical units, there existed a vast spherical cloud of icy objects. This cloud, he argued, was the reservoir from which long-period comets originate. Gravitational disturbances occasionally knock an object out of this cloud and send it on a long elliptical path that brings it plunging toward the inner solar system, where we observe it as a comet. This became known as the Oort Cloud. The idea was not merely speculative. It fit the observational data in a highly specific way. The spherical nature of the cloud explained why long-period comets arrived from all directions, not just from the plane of the solar system, like their short-period cousins. The distance range Oort estimated explained why the aphelia of observed comets clustered where they did. And the sheer number of long-period comets observed implied that whatever was out there must contain a truly enormous number of objects, likely numbering in the hundreds of billions or even trillions. So where did all of this material come from? The leading explanation connects the Oort cloud to the earliest period of our solar system's history, roughly 4.5 billion years ago. When the sun first formed, it was surrounded by a rotating disk of gas and dust. Over millions of years, material within this disk clumped together to form the planets. But not everything became a planet. Enormous quantities of leftover material, rocky and icy chunks called planetesimals, remained scattered throughout the young solar system. As the giant planets, particularly Jupiter and Saturn, grew and settled into their orbits, their immense gravitational influence began reshuffling everything around them. Planetesimals were flung in every direction. Some were hurled directly out of the solar system entirely, lost to interstellar space, but a significant portion were sent into highly elongated, eccentric orbits that kept them gravitationally bound to the sun while flinging them to enormous distances. At those enormous distances, the gravitational influence of the sun weakens considerably. Other forces begin to matter. The gravity of nearby stars, the gravitational pull of giant molecular clouds drifting through the galaxy, and even the tidal forces generated by the mass of the entire Milky Way galaxy all begin to affect the trajectories of these distant objects. Over billions of years, these gentle perturbations gradually reshaped the orbits of scattered planetesimals, rounding them out and distributing them in a spherical shell rather than a flat disk. This is how astronomers believe the Oort cloud came to be. It is essentially the ancient debris of planetary formation, shuffled to extreme distances by the gravity of the young giant planets, and then further sculpted over billions of years by the gravitational environment of the galaxy. The Oort cloud likely has two distinct regions. The inner region, sometimes called the Hills cloud, after the astronomer Jack Hills, who first proposed it in detail, may be structured more like a thick disk rather than a complete sphere. This inner region extends from roughly 2,000 astronomical units out to around 20,000 astronomical units. The outer region, from around 20,000 to 100,000 astronomical units, is the more classically spherical shell that Oort originally envisioned. The outer boundary of the Oort cloud, at 100,000 astronomical units from the Sun, translates to roughly 1.5 light years. The nearest star system to our own, the Alpha Centauri system, lies approximately 4.25 light years away. This means the Oort cloud extends about a third of the way to our nearest stellar neighbor. It is, by any measure, a structure of extraordinary scale. To appreciate how far away even the inner edge of the Oort cloud is, consider the Voyager spacecraft. Both Voyager 1 and Voyager 2 were launched in 1977 and are the most distant human-made objects in the universe. Voyager 2, as of recent measurements, has traveled approximately 139 astronomical units from the Sun, moving at roughly 56,000 kilometers per hour. Voyager 2 crossed the boundary of the heliosphere, the region dominated by the solar wind, in November 2018. It is now officially in interstellar space. But even traveling continuously at 56,000 kilometers per hour, Voyager 2 would need approximately 300 more years just to reach the inner edge of the Oort cloud. And passing through the entire cloud, that journey, at the same speed, would take roughly 30,000 years. What causes Oort cloud objects to be deflected toward the inner solar system in the first place? Several mechanisms contribute. Passing stars can gravitationally disturb the outer Oort cloud as they travel through the galactic neighborhood. When a star comes close enough, its gravity can perturb thousands or even millions of Oort cloud objects, sending some of them on new trajectories that bring them toward the Sunday. The Milky Way's galactic tide, a large-scale gravitational effect generated by the mass distribution of the entire galaxy, also acts on the distant objects in the cloud, steadily tugging them and altering their orbital inclinations over long timescales. Giant molecular clouds, vast concentrations of gas and dust that drift through the galaxy, can have similar effects when the solar system passes through or near one. A notable example of stellar perturbation occurred approximately 70,000 years ago. A low-mass binary star system called Scholz's star passed through the outer edges of the Oort cloud. Scholz's star consists of a red dwarf paired with a brown dwarf companion, making it a relatively low-mass system. Because of this, Its gravitational influence was far weaker than the Sun's, and it did not cause any catastrophic disruption to the Oort cloud as a whole. However, numerical simulations published in 2018 suggest that Scholz's star's passage did nudge at least some Oort cloud objects out of their stable orbits, contributing to the creation of certain long-period comets that may now be traveling through the inner solar system. This is not a rare event on cosmic timescales. The Sun has existed for over 4 billion years, and in that time, many stars have passed through the galactic neighborhood at various distances. Each passing star can perturb the Oort cloud to some degree. Over geological timescales, this constant gentle harassment from passing stars may actually help replenish the supply of long-period comets, since each passage potentially dislodges a fresh batch of objects from their stable, distant orbits. There is another intriguing implication of these stellar interactions. If our Sun's Oort cloud can be perturbed by passing stars, and if those stars also have their own Oort-like clouds, then it is theoretically possible that material gets exchanged between stellar systems over time. Numerical simulations have indeed suggested that Oort clouds could exist around other stars, and that material from these distant reservoirs might occasionally become interchangeable as star systems pass near one another over billions of years. Our Oort cloud may contain not just primordial debris from our own solar system's formation, but also icy fragments that originated around other stars entirely. This idea gained vivid support in 2019 when amateur astronomer Gennady Borisov discovered an object traveling through our solar system on a hyperbolic trajectory, meaning it was moving too fast to be gravitationally bound to the Sunday. Subsequent analysis confirmed that this object, designated 2I/Borisov, was a comet that had originated in another star system entirely. It was the first confirmed interstellar comet ever detected. Professional astronomers quickly mobilized to study it. Detailed spectroscopic analysis revealed an unusual composition. 2I/Borisov contained a higher concentration of carbon monoxide than typical comets originating from our solar system. This difference in chemistry suggested it may have formed in the presence of a red dwarf star, a type of star cooler and dimmer than our Sunday. The object was, in every measurable sense, alien. It had spent billions of years traveling through interstellar space before briefly passing through our solar neighborhood and continuing on its journey. The detection of 2I/Borisov demonstrated something important. Interstellar comets do exist. Objects do travel between star systems. The galaxy is not a collection of isolated, hermetically sealed solar systems. Material can and does migrate between them, albeit over astronomically long timescales. This does complicate the picture slightly when it comes to the Oort cloud. Some scientists have argued that if interstellar comets are real and detectable, perhaps some long-period comets that astronomers have attributed to the Oort cloud actually originated from other star systems. This would potentially mean the Oort cloud is not solely responsible for all observed long-period comets, or that its apparent size and population, as inferred from comet observations, might be slightly different from reality. However, the vast majority of professional astronomers continue to support the Oort cloud theory as the primary explanation for long-period comets. The indirect evidence is extensive, the mathematical models are consistent, and no alternative explanation accounts for all of the observed characteristics of long-period comets as elegantly as the Oort cloud hypothesis does. So why have we never directly observed the Oort cloud, despite living in an era where our telescopes can image galaxies billions of light years away? The answer comes down to two fundamental challenges: distance and reflected light. Telescopes detect objects either because they emit light, like stars, or because they reflect light, like planets and smaller bodies in our solar system. The planets are visible because sunlight reaches them and bounces back toward Earth with enough intensity to be detected. Even the asteroid belt and the Kuiper Belt, though faint, are close enough to the Sun that sunlight still illuminates their debris sufficiently for telescopic detection. The Oort cloud is different. At its inner edge, 3,000 or more astronomical units from the Sun, the intensity of sunlight is reduced to an extraordinarily faint level. At 50,000 astronomical units, the distance at which most long-period comet aphelia cluster, sunlight is reduced by a factor of 2.5 billion compared to its intensity at Earth's distance from the Sunday. An individual Oort cloud object is estimated to be roughly the size of a mountain, perhaps comparable to a body like Mount Everest in volume. At a distance of 3,000 astronomical units from the Sun, the nearest possible Oort cloud object would be about 50 million times farther from us than its own size. The reflected sunlight from such an object would be utterly undetectable with any current or near-future telescope. This is the core observational challenge. The Oort cloud is not hidden because it is physically blocked from our view. It is hidden because its objects are simultaneously very distant, very small relative to that distance, and illuminated by sunlight that has been diluted to almost nothing by the time it reaches them. There is also the sheer size of the sky to contend with. Even if we could detect individual Oort cloud objects, they are spread across an enormous three-dimensional volume of space. Finding them would require scanning not just the flat disk of the sky where the planets and Kuiper Belt objects are found, but the entire celestial sphere in 3 dimensions, at distances that challenge the limits of any conceivable observational technology. Mathematical models, however, have consistently supported the Oort cloud's existence. Computer simulations of early solar system evolution, when provided with realistic initial conditions, naturally produce a population of objects distributed in a region that matches Oort's theoretical description. The orbital characteristics of long-period comets, including their aphelia distances, their inclination distributions, and their arrival frequencies, all fit predictions derived from Oort cloud models. The agreement between theory and observation is not perfect, since nature never is, but it is strong enough that astronomers treat the Oort cloud's existence as effectively certain, even without direct detection. This situation has historical precedent. Scientists have often been highly confident in the existence of things they could not directly observe. In the 16th and 17th centuries, Copernicus and Galileo advanced the heliocentric model of the solar system, arguing that Earth and the other planets orbit the Sun, not the other way around. They could not directly see Earth moving through space. Their evidence was indirect, derived from careful observation of planetary motions. But the indirect evidence was compelling enough that the theory prevailed, and subsequent observations confirmed it completely. Similarly, the existence of atoms was disputed well into the 20th century, because nobody had ever directly seen one. Yet the indirect evidence from chemistry, thermodynamics, and other fields was overwhelming. Once technology advanced sufficiently, direct imaging of individual atoms became possible, confirming what indirect evidence had long suggested. The Oort cloud may follow a similar trajectory. It exists at a distance and scale that current technology cannot directly probe. But the indirect evidence has accumulated steadily over 7 decades since Oort first proposed the idea. And every new observation of long-period comets, every new computer simulation of solar system formation, and every new detection of perturbative forces acting on distant solar system objects adds another data point in support of the theory. There are still significant open questions. The exact population of the Oort cloud remains uncertain. Estimates of the total number of objects range from a few hundred billion to several trillion, but pinning down that number more precisely requires better models of how efficiently objects get scattered to Oort cloud distances during planetary formation, and how efficiently they get perturbed back into the inner solar system afterward. Different assumptions about these processes lead to different population estimates. The inner boundary of the Oort cloud also remains uncertain. The Hills cloud, the inner disk-like region, is even harder to study than the outer spherical shell because its objects are less susceptible to the galactic perturbations that send outer Oort cloud objects sunward. The inner cloud may be much more densely populated than the outer cloud, functioning as a reservoir that slowly replenishes the outer cloud, as the outer cloud's population is depleted by cometary losses and stellar perturbations. There is also an ongoing question about whether the Oort cloud's composition varies across its volume. Objects formed in different parts of the early solar system before being scattered outward would have different chemical compositions depending on how close to the Sun they originally formed. Objects that formed near Jupiter or Saturn might be richer in volatile compounds than objects scattered from the inner solar system. If this compositional gradient exists and is preserved in the Oort cloud, studying the compositions of long-period comets in detail could provide a window into the early chemical structure of the solar system. Future observatories and detection methods may begin to chip away at these questions. The Vera C. Rubin Observatory, currently being commissioned in Chile, will conduct a decade-long survey of the sky with unprecedented depth and coverage. While it is unlikely to detect actual Oort cloud objects at their distant resting places, it will detect many new long-period comets as they swing through the inner solar system. Each new comet adds to the statistical database from which Oort cloud properties can be inferred. Space telescopes operating at infrared wavelengths may eventually be able to detect the faint thermal emission from Oort cloud objects, since even at their extreme distances, these bodies are slightly warmer than the surrounding near absolute zero interstellar environment. However, this remains a significant technological challenge that no current mission is designed to meet. There is also the possibility of an interstellar mission, a spacecraft sent deliberately on a trajectory that would take it through the Oort Cloud over the course of centuries or millennia. While no such mission is planned, or near-term feasible given current propulsion technology, long-term space exploration concepts sometimes include such ideas. A spacecraft that could travel at a significant fraction of the speed of light, well beyond current capabilities, could in principle reach the Oort Cloud's inner edge within a human lifetime. The technological barriers to such a mission are immense, but not considered fundamentally impossible by physicists thinking about long-term human civilization. For now, the Oort Cloud remains one of the most fascinating theoretical structures in modern astronomy. It represents the outer boundary of our solar system's gravitational domain, the farthest region where objects remain captured by the sun's gravity. It is a fossil record of the earliest era of planetary formation, a region where ancient icy planetesimals have been preserved in a deep freeze for 4.5 billion years. It is the source of some of the most spectacular objects visible to the naked eye. Long-period comets that arrive from deep space streak across the inner solar system in a blaze of gas and dust, and then retreat back to the frozen darkness for millions of years. Beyond the Oort Cloud, the sun's gravitational hold gives way entirely to interstellar space. The nearest star system, Alpha Centauri, is roughly 4 light-years away, which means that approximately 2.5 light-years of essentially empty interstellar space separates our Oort Cloud from whatever structures surround our nearest stellar neighbors. If those stars have their own Oort-like clouds, which theoretical models suggest they should, then there may be a gap of roughly 1 light-year between the outer edges of our two systems. This gap, these vast stretches of dark interstellar space between stellar systems, is one reason interstellar travel is such a profound challenge. The Oort Cloud's outer edge is only 1.5 light-years away, but reaching it at current spacecraft speeds would take tens of thousands of years. Crossing the remaining 2.5 light-years to Alpha Centauri would take many more. The distances are not merely large. They are of a fundamentally different order of magnitude than anything encountered within the inner solar system. What the Oort Cloud ultimately represents, scientifically and conceptually, is the edge of home. It is the outermost boundary of the system in which Earth formed, in which life evolved, in which human civilization arose and began to look outward. Everything inside the Oort Cloud is, in some sense, local. Everything outside is, in equally real sense, somewhere else entirely. That boundary is invisible to us with current technology. We know it is there because the comets tell us so, because the mathematics of gravity and orbital mechanics require it, and because every model of solar system formation that produces a solar system resembling ours also produces a structure resembling the Oort Cloud. The evidence is indirect, but it is deep, consistent, and growing. In the history of science, that combination has almost always been sufficient. To fully appreciate the scale of the Oort Cloud and what it means for our understanding of the solar system, it helps to walk through the solar system from the inside out, building up a sense of the distances involved before arriving at the outermost frontier. Earth is 1 astronomical unit from the Sunday Mars. Our nearest outer planetary neighbor orbits at roughly 1.5 astronomical units. The asteroid belt, the broad ring of rocky debris between Mars and Jupiter, spans from about 2 astronomical units to about 3.5 astronomical units. Jupiter itself orbits at 5.2 astronomical units, Saturn at 9.5 astronomical units, Uranus at 19 astronomical units, and Neptune at 30 astronomical units. These numbers scale in ways that can be hard to hold in the mind simultaneously. If you place the Sun at one end of a football field, Earth would be about 1 yard from the Sunday. Mars would be 1.5 yards away. Jupiter would be 5 yards away. Neptune would be 30 yards away. Pluto, which orbits in the Kuiper Belt region at an average of about 39 astronomical units, would be roughly 39 yards from the Sunday. The main Kuiper Belt would extend to about 50 yards, its scattered disk out to about 1,000 yards, which is nearly 9 football fields. But the inner edge of the Oort Cloud would be at 2,000 yards from the Sun, over 1.25 miles, and the outer edge, at 100,000 astronomical units, would be 100,000 yards away, more than 56 miles. This analogy illustrates just how different the Oort Cloud is in scale from everything else in the solar system. It is not merely a distant extension of the planetary system. It is a structure that dwarfs everything else, combined by an enormous margin. The total mass of the Oort Cloud is also a subject of ongoing scientific interest and uncertainty. Current estimates suggest the total mass of material in the Oort Cloud could be anywhere from a few times the mass of Earth up to several tens of times the mass of Earth, depending on how many objects it contains and their typical sizes. If the population is toward the higher end of estimates, trillions of objects, and if many of those objects are substantially sized, then the total mass could be quite significant by solar system standards. For comparison, Jupiter, the most massive planet in the solar system, contains more than 300 times the mass of Earth. So even on the highest estimates, the Oort Cloud's total mass is still a small fraction of Jupiter's mass. The individual objects in the Oort Cloud are not especially large. Most are thought to be small bodies, ranging from perhaps a kilometer across to perhaps tens or hundreds of kilometers in their largest dimensions. But the estimated population in the trillions makes the total inventory substantial, even with modest individual sizes. The composition of Oort Cloud objects is inferred largely from the comets that originate there. When a long-period comet swings close to the Sun, the heat causes its surface ices to sublimate, releasing gas and dust in the characteristic coma and tail that make comets so visually striking. By studying the spectral signatures of these gas and dust emissions, astronomers can determine what compounds are present. Long-period comets typically contain water ice in large quantities, as well as carbon dioxide, carbon monoxide, methane, and various organic compounds. The presence of organic molecules in comets has long fascinated scientists, because these are the kinds of molecules that are relevant to the chemistry of life. Some researchers have speculated that cometary impacts in Earth's early history may have delivered significant quantities of water and organic material to the planet's surface, potentially contributing to the conditions that allowed life to emerge. If long-period comets indeed originate in the Oort Cloud, and if their compositions are representative of Oort Cloud material, then the cloud contains vast quantities of these compounds, preserved in a deep freeze for billions of years. The Oort Cloud is, in this sense, a kind of time capsule, preserving a chemical record of the material that existed in the outer solar system shortly after the planets formed, before geological processes, solar radiation, and other factors altered the compositions of bodies closer to the sunday. One of the most scientifically compelling aspects of Oort Cloud research involves understanding the rate at which comets are delivered from the cloud to the inner solar system. This rate is not constant. It can vary significantly, depending on the strength of galactic perturbations at any given time. As our solar system orbits the center of the Milky Way, it oscillates up and down through the galactic plane on a timescale of roughly 30 to 40 million years. When the solar system passes through the denser midplane of the galaxy, gravitational tidal forces from the concentrated mass of stars and gas are stronger, potentially enhancing the rate at which Oort Cloud objects are perturbed and sent toward the inner solar system. This could mean that the Earth experiences periodic increases in the rate of comet impacts correlated with our solar system's orbital dynamics. Some researchers have looked for evidence of this in the geological record. The Earth has been struck by large impactors throughout its history, and some impact craters have been dated. A handful of studies have claimed to find a periodicity in the ages of large impact craters that might correspond to the galactic oscillation timescale, suggesting enhanced bombardment during certain phases of the solar system's galactic orbit. However, this hypothesis remains controversial. The geological record of impact events is incomplete, and statistical analyses of the available data have produced mixed results. The idea is scientifically plausible, but not yet established as a confirmed phenomenon. What is more clearly established is that specific events, like a star passing close to the solar system, can temporarily increase comet delivery rates. When a massive star passes within a few light years of the Sun, its gravity can strongly perturb the outer Oort Cloud, dislodging large numbers of objects and sending many of them on trajectories toward the inner solar system. This kind of event has been called a comet shower. A sufficiently dramatic comet shower, triggered by a close stellar passage, could potentially increase the rate of comet impacts on Earth by a factor of 10 or more for a period of millions of years. The geological and biological consequences of such an event would be significant. Increased bombardment could affect climate through the injection of dust and debris into the atmosphere, could deliver additional water and organic material to the surface, and could trigger mass extinctions if the largest impactors struck. Some researchers have proposed that certain mass extinction events in Earth's history might be partially attributable to comet showers triggered by stellar perturbations of the Oort Cloud. The most famous mass extinction, the End Cretaceous event, 66 million years ago, that wiped out the non-avian dinosaurs, is attributed primarily to the impact of a large asteroid or comet. Whether Oort cloud dynamics played any role in that specific event is unclear, but the general principle that Oort cloud perturbation events could have influenced Earth's biological history is taken seriously by some researchers. Understanding the Oort cloud is therefore not purely an academic exercise in mapping the distant solar system. It has potential implications for understanding the conditions that have shaped life on Earth. The question of how the Oort cloud was initially populated is also more nuanced than the simple story of planetary formation and gravitational scattering might suggest. Early in the solar system's history, the young sun was part of a stellar cluster, a group of many stars that formed from the same molecular cloud and initially remained gravitationally associated. These stellar clusters are common in our galaxy, and observations of star-forming regions show that most stars form in such groups rather than in isolation. If the sun formed in a stellar cluster, then the early solar system was much more gravitationally complex than it is today. Multiple stars in close proximity would have created a rich environment of tidal forces and gravitational perturbations. Some researchers have proposed that these early cluster interactions were crucial for shaping the Oort cloud. Objects scattered by the giant planets to large distances would be much more easily captured into stable Oort cloud orbits if neighboring stars in the birth cluster helped round out their initially elongated trajectories. This mechanism, called cluster capture, might have been far more efficient than galactic tidal forces alone in populating the Oort cloud. The solar birth cluster eventually dispersed. Over hundreds of millions of years, the stars drifted apart under the combined influence of their own random motions and galactic tidal forces. By the time the solar system was 1 billion years old, most of the birth cluster stars would have been separated by many light years, effectively ending the strong gravitational interactions between them. But the material they helped capture into the Oort cloud during the cluster phase would remain in place for billions of years afterward. This hypothesis has implications for the Oort cloud's composition. If material from neighboring stars in the birth cluster was occasionally captured into our Oort cloud during the cluster phase, then the cloud might contain some objects that originally formed around different stars. Conversely, material from our protosolar disk might have been captured by neighboring stars and incorporated into their own Oort-like clouds. The solar birth cluster could have facilitated an early exchange of material between stellar systems, blurring the compositional distinctions between them. Detecting evidence of such exotic material in the Oort cloud, if it exists, would require detailed chemical analysis of many long-period comets to identify those with compositions that differ significantly from what is expected for objects formed in our own solar system. The detection of 2I/Borisov in 2019 showed that interstellar material can be distinguished from local material through spectroscopic analysis, suggesting this kind of detective work is at least, in principle, possible. Another dimension of Oort cloud science involves its long-term stability and evolution. The cloud is not static. Over billions of years, the combined effects of galactic perturbations, stellar flybys, and the gradual loss of comets ejected from the cloud permanently into interstellar space, or destroyed by solar heating when they swing too close to the sun, all contribute to a slow depletion of the cloud's population. At the same time, the cloud may be replenished to some degree by material scattered outward from the Kuiper Belt and the scattered disk when those regions are perturbed by gravitational interactions within the solar system. There may also be ongoing capture of interstellar material into the Oort cloud, though the efficiency of this process is thought to be low under current conditions compared to what it might have been during the solar birth cluster phase. The net result is that the Oort cloud's population is probably declining slowly over geological timescales. The cloud is estimated to have contained considerably more material early in the solar system's history than it does today. Models suggest that the inner solar system experienced a much higher rate of long-period comet impacts billions of years ago when the Oort cloud was more densely populated. This era of heavier bombardment overlaps with what is known as the Late Heavy Bombardment, a period approximately 3.9 billion years ago when the inner solar system, including the Moon and Earth, experienced an elevated rate of large impacts. The origin and nature of the Late Heavy Bombardment remains one of the more actively debated topics in planetary science. Some models suggest it was caused primarily by disruption of the asteroid belt due to migration of the giant planets. Others invoke outer solar system dynamics, including Kuiper Belt and Oort Cloud perturbations. The truth may involve contributions from multiple sources. What is clear is that the early Earth experienced an intense period of impacts that would have had profound effects on the planet's surface and potentially on the emergence and early evolution of life. The Oort Cloud's role in this broader story of solar system evolution illustrates why understanding it is not simply about characterizing a remote and exotic structure at the solar system's edge. The cloud is connected through the mechanics of gravity and orbital dynamics to the history of every body in the solar system, including Earth itself. Looking forward, the scientific study of the Oort Cloud will continue to progress primarily through indirect means, at least for the foreseeable future. Each new long-period comet discovered and characterized adds data points to the statistical distribution that constrains Oort Cloud models. Each new numerical simulation of solar system formation refines our understanding of how the cloud formed and how its current properties should be expected to compare to the initial state. The development of more powerful survey telescopes will accelerate the rate of long-period comet discovery. Where astronomers in earlier eras might have cataloged a few dozen well-characterized long-period comets over decades of observing, future surveys may catalog thousands per year. This statistical windfall will allow far more precise measurements of the distribution of cometophilia, the distribution of orbital inclinations, and the range of compositional types among long-period comets, all of which constrain the properties of the Oort Cloud from which they originate. Advanced spectroscopic analysis of cometary compositions will increasingly allow astronomers to distinguish different populations within the long-period comet reservoir. Some comets may have compositions that suggest formation closer to the Sun before being scattered outward, while others may have compositions indicative of formation in the outer solar system. Still others, like 2I/Borisov, may turn out to be interstellar visitors, entirely unrelated to our own Oort Cloud. Building a catalog rich enough to distinguish these populations statistically will reveal information about the Oort Cloud structure and history that cannot be obtained any other way. There is also growing interest in searching for objects in the transitional zone between the Kuiper Belt's scattered disk and the inner Oort Cloud. A handful of unusual objects have been discovered in the past 2 decades that orbit at distances and inclinations inconsistent with being part of the classical Kuiper Belt, but far too close to the Sun to be genuine Oort Cloud members. These objects, sometimes called Sedna-like objects after the distant body Sedna discovered in 2003, may represent the inner edge of the Hills cloud, or may be evidence of additional structures in the trans-Neptunian region that are not yet well understood. Sedna itself orbits at distances ranging from about 76 astronomical units at its closest to roughly 1,000 astronomical units at its farthest, with an orbital period of approximately 11,000 years. Its orbit is far too distant and eccentric to be explained by current planetary perturbations. Some researchers have proposed that Sedna's unusual orbit was shaped by gravitational interactions during the solar birth cluster phase, when neighboring stars could have influenced the outer solar system much more strongly than any force acting today. Others have proposed that a distant, undiscovered planet in the outer solar system might be responsible for sculpting Sedna's orbit and those of similar objects. The hypothesis of a large undiscovered planet, sometimes called Planet 9, has attracted considerable attention in recent years. This hypothetical world, if it exists, would orbit at hundreds to thousands of astronomical units from the Sun, placing it in or near the inner Oort Cloud region. Its gravity could potentially explain several observed anomalies in the orbits of distant Kuiper Belt objects and Sedna-like bodies, and it would represent a dramatic discovery if confirmed. No direct evidence of Planet 9 has been found as of this writing, and the hypothesis remains controversial. Some astronomers argue that the orbital clustering of distant Kuiper Belt objects that motivated the Planet 9 hypothesis may be a statistical artifact of observational biases rather than a genuine signal. Others continue to find the hypothesis compelling and are actively searching for the proposed planet with current and upcoming survey facilities. If Planet 9 or any similarly large body were discovered in the inner Oort Cloud region, it would fundamentally reshape our understanding of the solar system's outer reaches. A massive planet at those distances would have significant gravitational influence on the Oort Cloud itself, potentially acting as a source of perturbations that sends inner Oort Cloud objects toward the inner solar system on a regular basis. It would also raise profound questions about how such a body came to be so far from the Sun, whether through scattering by the giant planets during planetary formation or through some other mechanism. The intersection of these various lines of inquiry, the study of long-period comets, the analysis of distant trans-Neptunian objects, the numerical modeling of solar system formation, the search for undiscovered outer solar system bodies, and the broader context of stellar dynamics and galactic tidal forces is what makes the Oort Cloud such a rich area of ongoing scientific investigation. It is a region we cannot see directly, but one that we can probe through careful observation and sophisticated modeling. Every comet that sweeps through the inner solar system is a messenger from the outer frontier, carrying chemical and dynamical information about the conditions at the solar system's edge and the forces that operate there. Reading these messages carefully and building up a coherent picture of what they collectively imply is the ongoing work of a field that has been active for over 7 decades and shows no signs of running out of questions. The Oort Cloud is the outermost layer of our home in the cosmos. It is ancient, vast, and almost entirely unknown in its details. It connects our solar system's deep past to its long future, and it connects our neighborhood to the broader stellar environment of the Milky Way. Understanding it more fully is one of the quietly profound challenges of modern planetary science, pursued not through dramatic discoveries, but through the steady accumulation of data, the refinement of models, and the patient interpretation of whatever signals these distant icy travelers choose to send our way. To understand the Oort Cloud's place in the broader context of solar system science, it helps to step back and consider the history of how astronomers have come to understand the solar system's structure over the past several centuries. For most of human history, the solar system was understood to consist of whatever was visible to the naked eye. The sun, moon, 5 planets, and the background stars were the totality of the known universe for thousands of years. The telescope changed this dramatically, beginning in the early 17th century. Galileo's observations of Jupiter's moons, Saturn's rings, and the phases of Venus revolutionized our understanding of the solar system structure and confirmed that Earth orbited the sun rather than the reverse. Over the following centuries, the telescope revealed a solar system far richer than previously imagined. Uranus was discovered in 1781 by William Herschel. Neptune was discovered in 1846 following mathematical predictions by Urbain Le Verrier and John Couch Adams, who inferred its existence from perturbations in Uranus's orbit. Ceres, the largest body in the asteroid belt, was discovered in 1801. Pluto was discovered in 1930. Each discovery expanded the known boundaries of the solar system, but telescopic technology and the sheer distances involved eventually created a boundary that visual observation alone could not cross. The Kuiper Belt was not confirmed observationally until 1992, when the object now called 1992 QB1 was discovered beyond Pluto. The Oort Cloud remains unconfirmed by direct observation to this day, a reminder that our knowledge of the solar system still has fundamental frontiers. This history also illustrates an important principle about scientific knowledge. We know the most about the parts of the solar system that are closest to us and that interact most readily with light. The inner solar system is well characterized. The outer solar system is progressively less well characterized as distance increases. The Oort Cloud represents the extreme end of this gradient, a region where our indirect methods of inference must do all the work that direct observation cannot. The mathematical and computational tools that allow us to model the Oort Cloud have themselves evolved dramatically over the past 7 decades. When Jan Oort proposed the cloud's existence in 1950, he was working with relatively limited computational resources by modern standards. His analysis was based on the orbital characteristics of a few dozen well-measured long-period comets, and his calculations were done largely by hand or with mechanical calculators. By the 1980s and 90s, computer simulations of solar system formation had become sophisticated enough to model the scattering of planetesimals by the giant planets over millions of years, and these simulations naturally produced populations of objects with Oort Cloud-like orbital distributions. This was a powerful independent line of support for the Oort Cloud theory, since it showed that the cloud was not just an ad hoc explanation for observed comets, but a natural consequence of well-understood processes of planetary formation and gravitational dynamics. Modern simulations are far more sophisticated still. They can track millions or even billions of individual test particles as they are scattered by the planets, perturbed by galactic tidal forces, and influenced by passing stars over the full 4.5 billion year history of the solar system. These simulations produce detailed predictions about the Oort Cloud's structure, composition, and evolution that can be compared with observations of long-period comets. The consistency between simulation predictions and observations has grown steadily stronger over the decades as both the simulations and the observational databases have improved. One of the persistent challenges in these simulations is that the efficiency of the processes that populate the Oort cloud is not perfectly understood. What fraction of the original planetesimal population ended up in the Oort cloud versus being ejected from the solar system entirely or remaining in the Kuiper Belt? Different simulations, with different assumptions about the initial conditions of the solar system and the migration history of the giant planets, produce different answers to this question. Getting the right answer matters because it determines the Oort cloud's total population and mass, which in turn affects predictions about the rate of long-period comet delivery to the inner solar system. The migration of the giant planets during the early solar system is itself a subject of intense research. There is strong evidence from the orbital distributions of Kuiper Belt objects, the irregular satellites of the giant planets, and the structure of the asteroid belt that Jupiter, Saturn, Uranus, and Neptune did not form in their current orbital positions. They likely formed closer to the Sun and migrated to their current orbits over millions of years through interactions with the disk of gas and smaller bodies that surrounded the young Sunday. The most widely discussed model of giant planet migration is called the Nice model, named after the city in France where it was developed by a team of researchers. In this model, the giant planets initially formed in a more compact configuration and then migrated outward as they exchanged angular momentum with the disk of small bodies surrounding them. Jupiter migrated slightly inward, while Saturn, Uranus, and Neptune migrated outward. At some point, Jupiter and Saturn reached a configuration where their orbital periods were in a simple ratio, called a resonance, which caused a dramatic instability. This instability scattered Uranus and Neptune outward violently, scattering enormous quantities of Kuiper Belt material throughout the solar system. Some of this scattered material was sent to the Oort cloud. Some impacted the inner planets, contributing to the late heavy bombardment. The Nice model and its successors have been remarkably successful at explaining a wide range of observed features of the solar system's architecture. However, different versions of these models produce somewhat different predictions about Oort cloud formation, and determining which version of the model is most accurate remains an active area of research. Another approach to understanding the Oort cloud involves looking at other planetary systems. The past 3 decades have seen an explosion in the detection and characterization of planets orbiting other stars. More than 5,000 exoplanets have now been confirmed, orbiting stars of every type in environments ranging from scorching proximity to their host stars to chilly distant orbits. This observational revolution has revealed that planetary systems come in an enormous variety of configurations, many of them quite different from our own solar system. If other stars have planetary systems, and if those systems have undergone formation processes similar to our own, then other stars should also have Oort-like clouds surrounding them. Detecting these extrasolar Oort clouds directly is even more challenging than detecting our own, since they are both farther away and smaller in angular size on the sky. However, some researchers have proposed that long-period comets arriving from the direction of other star systems, like 2I/Borisov, could be detected during their brief passages through the inner solar system, and characterized well enough to infer properties of their home Oort clouds. The detection and study of additional interstellar comets would provide a statistical sample of objects from Oort-like clouds around other stars. Comparing their compositions with those of our own long-period comets could reveal whether Oort clouds are compositionally similar across different stellar environments, or whether the details of planetary formation and stellar environment leave distinctive chemical fingerprints. There is also the question of what happens to the Oort cloud in the very long-term future. The Sun will not remain a stable main sequence star forever. In approximately 5 billion years, it will exhaust the hydrogen fuel in its core and expand dramatically, becoming a red giant star. During this phase, the Sun will swell to perhaps 100 times its current radius, engulfing the inner planets including Earth. Its outer layers will be expelled gradually into space in what astronomers call a planetary nebula. The remains of the Sun will become a white dwarf, a compact object perhaps the size of Earth, but still containing about half of the Sun's original mass. The white dwarf will be extremely hot initially, but will cool gradually over billions of years. The gravitational field of the white dwarf will be reduced compared to the original Sun's gravity, since it will contain less mass, and this reduction in gravity will cause all of the surviving outer solar system bodies to drift to larger orbits. The Oort cloud, if it survives the Sun's red giant phase more or less intact, will expand to even larger distances around the white dwarf and become increasingly susceptible to perturbation by passing stars. Some research suggests that white dwarf stars are often found to have substantial amounts of rocky or icy material in their atmospheres, accreted from the remains of their own planetary systems. The infrared excesses observed around many white dwarfs indicate the presence of dusty debris disks, and spectroscopic observations show heavy elements in white dwarf atmospheres that must have been delivered recently by accreting solid material. The Oort Cloud analogs of these systems may be providing some of this accreting material as their orbits become increasingly perturbed in the changed gravitational environment of the white dwarf phase. This is a sobering long-term picture, but it also illustrates how intimately the fate of the Oort Cloud is tied to the fate of the Sunday. The cloud formed from the debris of solar system formation has been slowly sculpted by the Sun's gravity and external galactic forces for 4.5 billion years, and will eventually be dispersed as the Sun enters its final evolutionary stages. On geological timescales, the Oort Cloud is ancient and stable. On cosmological timescales, it is a temporary structure like everything else in the universe. For now, in the present era of the solar system's history, the Oort Cloud sits in its dark, cold silence. Billions or trillions of icy bodies, each one a relic of the solar system's birth, move in their slow, enormous orbits at distances that challenge human comprehension. Occasionally, a gravitational nudge from a passing star, a molecular cloud, or the gentle tidal pull of the galaxy sends one of these ancient objects on a new trajectory, beginning a journey that will take millions of years to complete. If that journey brings the object toward the inner solar system, and if it survives intact long enough to round the Sun, we may see it as a long-period comet, its ancient ice sublimating in the solar heat to produce a spectacular display visible from Earth. In that moment, an object that has been frozen in darkness at the edge of interstellar space since before any life existed on Earth briefly becomes visible to human eyes. It is a bridge across geological time, a physical connection between the present day and the solar system's ancient past. The light reflected from that comet carries information about conditions 4.5 billion years ago, encoded in the composition of ices that have been preserved unchanged at temperatures near absolute zero for the entire history of complex life on this planet. This is part of what makes the Oort Cloud so scientifically compelling and humanly fascinating. It is not just a distant structure at the edge of the solar system. It is a time capsule, a messenger system, and a marker of boundaries both physical and intellectual. It marks the boundary between our solar system and interstellar space. It marks the boundary between what we can directly observe and what we can only infer. And in its very inaccessibility and vastness, it reminds us how much of even our own cosmic neighborhood remains genuinely unknown. The study of the Oort Cloud is, in a deep sense, the study of limits. The limits of our telescopes, the limits of our spacecraft, the limits of our computational models, and ultimately, the limits of our ability to know with certainty things that lie beyond the reach of direct experience. Science has a long and successful history of working productively within such limits, using indirect evidence, mathematical reasoning, and careful inference to build confident knowledge about things that cannot be directly touched or seen. The Oort Cloud sits at the far edge of what we know, in the twilight zone between confirmed knowledge and informed inference. Every new comet that arrives from its depths, every new simulation that refines our understanding of how it formed and evolves, and every new detection of material in interstellar space that might be connected to Oort-like structures around other stars brings us incrementally closer to a full understanding of this vast and ancient structure. We may never see the Oort Cloud directly with our own telescopes. We may never send a spacecraft through it in any individual human lifetime, but the work of understanding it continues, patient and cumulative, building piece by piece a picture of the outermost frontier of the world we call home. To appreciate the scientific process that led to and continues to refine the Oort Cloud theory, it is worth spending more time with the man who proposed it and the intellectual environment in which he worked. Jan Hendrik Oort was born in 1899 in the Netherlands. He studied astronomy at the University of Groningen under the supervision of Jacobus Kapteyn, one of the leading astronomers of the early 20th century. Kapteyn himself was known for his attempts to map the structure of the Milky Way, work that Oort would later build on and substantially correct. Oort's early career was marked by a remarkable combination of theoretical insight and observational rigor. In 1925, working from radial velocity measurements of stars, he demonstrated that the galaxy was rotating differentially, meaning that stars at different distances from the galactic center orbit at different speeds. This was a fundamental confirmation of the structure of our galaxy, and established that the Sun was located far from the galactic center in an outer region of the Milky Way. The mathematical relationships he derived to describe this differential rotation are still taught in astronomy courses today and are known as Oort's constants. His work on dark matter came in 1932, when he analyzed the vertical motions of stars near the Sun and found that the observed stellar density alone could not account for the gravitational force needed to explain those motions. He inferred that additional unseen mass must be present in the galactic disk. This was one of the earliest quantitative arguments for the existence of what we now call dark matter, though its true nature as exotic non-baryonic matter was not understood until decades later. Against this background of major astronomical contributions, Oort's 1950 paper on the origin of long-period comets reads as another example of his characteristic approach: careful data analysis, systematic identification of patterns, and the willingness to propose a theoretical structure that explained the patterns even when direct evidence for that structure was unavailable. The paper itself was relatively compact, presenting the statistical analysis of cometophilia and the theoretical argument for a surrounding cloud of icy objects in a clear and focused manner. Oort was not given to excessive speculation, and he was careful to distinguish between what the data directly showed and what could be inferred from it. The paper acknowledged that the proposed cloud had not been, and might not be directly observed, but argued that its existence was the most economical explanation for the observed properties of long-period comets. The response from the astronomical community was largely positive, though some skepticism remained. Oort's reputation was such that his theoretical proposals were taken seriously, and the internal consistency of his argument was evident. Over the following decade, the Oort cloud hypothesis became increasingly accepted as the standard explanation for long-period comets, even as direct observational confirmation remained elusive. The naming of the structure after Oort is somewhat ironic, given that similar ideas had been proposed earlier by Ernst Öpik, an Estonian astronomer, who in 1932 had suggested that comets originated from a distant cloud of icy objects surrounding the solar system. Öpik's paper preceded Oort's by 18 years, but it received less attention and was not developed into the detailed theoretical framework that Oort constructed. In some astronomical literature, the structure is therefore called the Öpik-Oort cloud, in acknowledgement of both contributions, though Oort's name alone is more commonly used. Oort continued to make significant contributions to astronomy until late in his life. He died in 1992 at the age of 92. Having lived long enough to see his Oort cloud theory become a standard component of solar system science, supported by decades of mathematical modeling and observational inference, even without direct detection. The parallel between the Oort cloud and other historically important invisible structures in science is worth exploring. Throughout the history of science, proposed structures that could not be directly observed, but could be inferred from their effects, have played a central role in advancing understanding. Black holes are perhaps the most familiar example. The theoretical prediction of black holes followed almost immediately from Einstein's general theory of relativity, published in 1915. A solution to Einstein's field equations found by Carl Schwarzschild just weeks after Einstein's paper showed that sufficiently compact masses would curve space-time so severely that nothing, not even light, could escape from within a certain radius. For decades, black holes were purely theoretical objects, inferred from the mathematics of general relativity, but with no direct observational evidence. The evidence for black holes accumulated gradually over many decades. Observations of X-ray binaries in the 1960s and 70s revealed stellar mass black holes accreting gas from companion stars. Observations of the motions of stars near the center of the Milky Way in the 1990s and 2000s confirmed the existence of a supermassive black hole at the galactic center, with a mass of roughly 4 million times the mass of the Sunday. And in 2019, the Event Horizon Telescope collaboration produced the first direct image of a black hole, the supermassive black hole at the center of the galaxy, M87, at a distance of 55 million light-years. Neutrinos provide another example. Wolfgang Pauli proposed the existence of neutrinos in 1930 to explain apparent violations of energy conservation in radioactive beta decay. For 2 decades, neutrinos remained purely theoretical, inferred from the missing energy in beta decay, but never directly detected. In 1956, Clyde Cowan and Frederick Rines finally detected neutrinos experimentally, confirming Pauli's prediction. In both cases, and in many others throughout scientific history, the pattern is the same. A theoretical entity is proposed because it is needed to explain observed phenomena. Indirect evidence accumulates over years or decades. Eventually, either direct detection is achieved, or the indirect evidence becomes overwhelming enough that the entity's existence is effectively certain even without direct observation. The Oort cloud fits this pattern. Oort proposed it because it was needed to explain long-period comets. Decades of accumulated indirect evidence, from comet orbital statistics, from computer simulations, from observations of related phenomena, have made its existence effectively certain in the judgment of the astronomical community. What remains uncertain is not whether it exists, but what its detailed properties are. The question of whether direct detection will ever be achieved is interesting to consider. With current telescope technology, individual Oort cloud objects at their resting distances are far too small and dark to be detected. But telescope technology continues to advance. The James Webb Space Telescope, launched in late 2021 and operational from 2022, operates primarily in infrared wavelengths with unprecedented sensitivity. It has already revealed details of the early universe, nearby star systems, and solar system objects that were previously inaccessible. However, it is not optimized for detecting very faint, very distant solar system objects, and the survey speed needed to search the enormous area of sky containing the Oort cloud is not among its primary capabilities. Future space telescopes might conceivably be designed with Oort cloud detection in mind. A large, space-based infrared survey telescope, with the ability to detect very faint thermal emission from cold bodies at extreme distances, could in principle find individual Oort cloud objects. The sensitivity required would be extraordinary, but it is not obviously beyond the reach of technology that might be achievable in the coming decades. There have also been more speculative proposals for detecting the Oort cloud through its gravitational effects. A sufficiently dense concentration of mass, at distances of a few thousand to 100,000 astronomical units, might produce subtle effects on the trajectories of spacecraft in the outer solar system, or on the timing of signals from pulsars. These effects would be extraordinarily small and difficult to detect over the background noise of other gravitational influences. But the principle is sound. Gravity is in principle detectable even when its source is invisible. The prospect of future space missions to the outer solar system also periodically enters discussions of Oort cloud science. No mission to the Oort cloud is in development, and the timescales and costs involved in getting a spacecraft to even the inner Oort cloud are prohibitive with current technology. A spacecraft traveling at the speed of Voyager 2 would need roughly 300 years just to reach the inner Oort cloud's edge, and the Oort cloud extends for another 30,000 years of travel time beyond that. Advanced propulsion concepts, such as nuclear pulse propulsion, laser sail technology, or antimatter drives, could in principle drastically reduce travel times to the outer solar system, and even to the Oort cloud. Some of these concepts are at early stages of theoretical and experimental development. The Breakthrough Starshot initiative, for example, is exploring the concept of laser-propelled light sail spacecraft that could theoretically travel at a few % of the speed of light, enough to reach the nearest star system in a few decades. A version of this technology, optimized for solar system exploration rather than interstellar travel, could potentially send probes to the inner Oort cloud within decades rather than centuries. However, the scientific return from such a mission would be limited by the extreme sparseness of the Oort cloud. Even with the estimated population of hundreds of billions of objects, the average distance between neighboring objects in the cloud is enormous. A probe sent to the inner Oort cloud would almost certainly not encounter any individual object, unless it was targeted toward one based on prior observations. The cloud is not like a dense asteroid belt where objects can be easily found. It is a vast, sparse haze of small bodies separated by distances vastly greater than the distances between planets. The most productive near-term approach to understanding the Oort cloud therefore remains the analysis of long-period comets as they arrive in the inner solar system. Each comet is essentially a free sample from the Oort cloud, delivered by the mechanics of orbital dynamics to a location where our instruments can study it in detail. The challenge is to extract as much information as possible from these samples, and to build an increasingly accurate statistical model of the population they come from. This requires careful measurement of comet orbits to determine their original orbital parameters before they were modified by the gravity of the inner planets. It requires detailed, spectroscopic analysis of comet compositions to build a catalog of the chemical diversity present in the Oort cloud. It requires tracking the rate of long-period comet discoveries over time to understand whether that rate is changing, which could indicate changes in the rate of perturbation from the galactic environment. And it requires sophisticated statistical analysis of all this data to extract reliable inferences about the Oort Cloud's structure and properties. The data collection side of this enterprise is accelerating. Modern automated sky surveys, designed to detect near-Earth asteroids and other transient phenomena, also detect many new comets as a byproduct. The Pan-STARRS survey, the Catalina Sky survey, and other programs have dramatically increased the rate of comet discovery compared to earlier eras. The Vera-C, Rubin Observatory's legacy survey of space and time, which will begin full science operations in the coming years, is expected to detect hundreds of new comets per year, including many long-period comets that will provide fresh data on the Oort Cloud. Data analysis capabilities have also advanced dramatically. Machine learning techniques can now be applied to large comet datasets to identify patterns and correlations that would be difficult to find through traditional statistical methods. These tools may reveal subtleties in the distribution of long-period comet orbital parameters that provide clues to the Oort Cloud's structure and to the detailed history of perturbations it has experienced. The connection between the Oort Cloud and the broader study of planetary system formation and evolution is worth emphasizing. The solar system is now known to be just one of hundreds of billions of planetary systems in the Milky Way alone. Understanding how our solar system formed and evolved, and how the Oort Cloud fits into that history, contributes to understanding planetary systems in general. The Oort Cloud is not just a feature of our solar system. It is likely a common feature of planetary systems throughout the galaxy, a natural consequence of the physics of planetary formation and gravitational scattering. As our ability to characterize other planetary systems improves, we may find indirect evidence for Oort-like structures around other stars. The detailed architecture of a planetary system, including the distribution of small bodies in its outer regions, reflects the history of the system's formation and dynamical evolution. Reading that architecture accurately requires understanding the full range of phenomena involved, including the formation and properties of structures analogous to our Oort Cloud. The study of debris disks around young and middle-aged stars provides some insights into this. Infrared observations of nearby stars frequently reveal the presence of circumstellar dust, inferred to result from ongoing collisions among smaller bodies in those systems. Some of this dust may be generated in regions analogous to our Kuiper Belt. Whether any of it comes from regions analogous to the Oort Cloud is harder to determine, since material at such extreme distances would produce an even fainter infrared signature. Polarimetry and other advanced observational techniques are being developed and refined to probe the outer regions of circumstellar environments around other stars. In the coming decades, these techniques may begin to provide observational evidence for or against the existence of Oort-like structures around specific nearby stellar systems, allowing direct comparisons between our solar system and its neighbors. Throughout all of this, the Oort Cloud remains what it has always been: a vast, silent, a frozen testament to the solar system's ancient history, and a quiet supplier of the occasional spectacular visitor to the inner solar system. It is a structure we understand imperfectly, observe indirectly, and may never visit directly. But it is unmistakably real as anything we know about the solar system, woven into the orbital fabric of the comets we observe and the mathematical structure of the models that describe them. Understanding the Oort Cloud also requires appreciating the physical environment in which it exists. The region of space occupied by the Oort Cloud is not empty, but it is extraordinarily sparse. The interstellar medium, the gas and dust that fills the space between stars, begins to influence conditions in the outermost Oort Cloud. At these distances, the density of the solar wind, the stream of charged particles constantly flowing outward from the sun, has become negligibly small. The heliosphere, the bubble of solar influence that contains the inner solar system, ends well before the Oort Cloud begins. Inside the heliosphere, the solar wind creates a protected environment that shields the inner solar system from the full intensity of the interstellar medium. The boundary of the heliosphere, called the heliopause, is where the solar wind's pressure is balanced by the pressure of the interstellar medium. Both Voyager spacecraft have crossed this boundary. Voyager 1 crossed it in August 2012, and Voyager 2 crossed it in November 2018. Both spacecraft are now traveling through true interstellar space, no longer bathed in the solar wind. But even the heliopause is at roughly 120 astronomical units from the sunday. The inner edge of the Oort Cloud is at 2,000 astronomical units or more. There is an enormous stretch of space, from the heliopause to the Oort Cloud's inner edge, that is neither truly inside the heliosphere nor part of the Oort Cloud proper. This region, sometimes informally called the outer heliosphere, or the very local interstellar medium, is a transitional zone where the sun's gravitational influence is still strong, but the solar wind's particle and field environment has been replaced by the interstellar medium. Objects in the inner Oort Cloud exist in this gravitational but not particle environment. They orbit the sun under gravity's influence, but they are not surrounded by the sun's solar wind or magnetic field. Instead, they are immersed in the interstellar medium, the diffuse collection of atoms, molecules, dust grains, magnetic fields, and cosmic rays that permeate the space between stars. The interstellar medium is far from uniform. Different regions of space between stars have different densities, temperatures, and compositions, depending on how they have been shaped by nearby stellar activity. Regions near recently formed stars or supernova explosions tend to be hotter, more ionized, and less dense, while regions far from recent energetic events can be cooler, denser, and more neutral in character. Our solar system is currently traveling through a region of the local interstellar medium called the local bubble, a region of unusually low-density hot gas that was likely created by a series of supernova explosions that occurred nearby in the past few million years. The inner region of this bubble, called the local interstellar cloud, or the G cloud, is the immediate environment through which our solar system is moving. As the solar system moves through different regions of the interstellar medium over its galactic orbit, the properties of the medium surrounding the outer Oort cloud change. When the solar system enters a denser region of the interstellar medium, the extra pressure can compress the heliosphere somewhat, potentially affecting the sun's influence over the outer Oort cloud. When the solar system passes through or near giant molecular clouds, the strong gravitational tidal forces of these massive structures can strongly perturb the outer Oort cloud, dislodging many objects and sending them toward the inner solar system. Molecular clouds are regions of extremely dense interstellar gas, primarily molecular hydrogen, that are the sites of new star formation. They are far denser than the average interstellar medium, and their gravitational influence can be felt at considerable distances. Our solar system has likely passed through or near several molecular clouds over its 4.5 billion year history, and each encounter would have had significant effects on the Oort cloud. Some researchers have proposed that encounters with molecular clouds might account for some of the observed clustering of long-period cometophilia, since a cloud encounter would preferentially perturb objects in certain orbital configurations and send them toward the inner solar system in clusters rather than uniformly spread in time and direction. Testing this hypothesis requires detailed records of long-period comet orbital parameters over timescales long enough to see the statistical effects of such encounters, which is challenging given the completeness limitations of historical comet catalogs. The Sun's galactic orbit also carries it through regions of the galaxy with different stellar densities. In the denser stellar environment near the galactic midplane, stellar flybys are more frequent, and the cumulative effect of multiple weaker perturbations from many stars can be significant over geological timescales. The exact stellar encounter history of our solar system over 4.5 billion years is not precisely known, since stars move and their past positions can only be approximately reconstructed from their current positions and motions. However, catalogs of nearby stars with precisely measured positions and motions, particularly from the European Space Agency's Gaia satellite, which has measured positions and motions for more than 1 billion stars with extraordinary precision, have made it possible to reconstruct the recent stellar encounter history of our solar system with unprecedented accuracy. Analysis of Gaia data has identified dozens of stars that have passed within a few light years of the Sun in the past few million years, or will do so in the future. Each such encounter has the potential to perturb the outer Oort cloud to some degree. Scholz's star, the low-mass binary system that passed through the outer Oort cloud approximately 70,000 years ago, was identified as a significant recent encounter through this kind of analysis. The fact that its encounter distance was actually within the Oort cloud, rather than merely close to the solar system, makes it particularly interesting. Numerical simulations of its encounter suggest that it perturbed approximately 100,000 to a few million Oort cloud objects, some of which are now traveling toward the inner solar system on long-period cometary orbits. Identifying specific long-period comets that owe their current trajectories to Scholz's star's encounter is extremely challenging, since the perturbations it caused were small and the resulting orbital changes take millions of years to manifest as observable comets. However, researchers have proposed statistical methods that might, with sufficient data, identify a slight enhancement in the rate of long-period comet arrivals from certain directions that could be attributed to the Scholz's star encounter. Future stellar encounters will also affect the Oort Cloud. Analysis of Gaia data has identified several stars that will pass within a few light-years of the Sun in the next million years. While none of these are expected to penetrate as deeply into the Oort Cloud as Scholz's star did, they will still exert gravitational perturbations on its outer regions, potentially triggering additional comet showers in the distant future. The Sun's closest known future stellar encounter is with a star called Gliese 710, a dim orange star currently located about 63 light-years away. In approximately 1.3 million years, Gliese 710 is predicted to pass within about 10,000 to 15,000 astronomical units of the Sun, which would bring it well within the outer Oort Cloud. This encounter is expected to be more disruptive than Scholz's star's flyby, since Gliese 710 is estimated to be about 60% as massive as the Sun, giving it considerably more gravitational influence than the low-mass binary system that grazed the Oort Cloud 70,000 years ago. Simulations of the Gliese 710 encounter predict that it could dislodge millions of Oort Cloud objects, triggering a comet shower that would increase the rate of long-period comet arrivals in the inner solar system by a factor of perhaps 2 to 4 for a period of a few million years. This is not necessarily a catastrophic event for life on Earth, since the baseline rate of long-period comet impacts is low, and even a several-fold increase would likely not dramatically affect conditions on the planet's surface. But it is a reminder that the Oort Cloud is not static, and that its gravitational environment will change significantly over cosmic timescales. The long-term evolution of the Oort Cloud is also affected by the physics of what happens to comets that are sent toward the inner solar system. Not all objects perturbed from the Oort Cloud make it all the way to the inner solar system and become observable long-period comets. Many are perturbed into hyperbolic trajectories that send them flying out of the solar system entirely. Others are captured into more tightly bound orbits by gravitational interactions with the planets, becoming members of the scattered disk or Kuiper Belt, or even shorter period comets. And some eventually fall into the Sun, or are destroyed by tidal forces, or by the heat of solar radiation. Each time an Oort Cloud object is sent into the inner solar system, there is some probability that it will be permanently lost from the cloud, either by being ejected from the solar system, captured into a tighter orbit, or destroyed. Over billions of years, this attrition has depleted the Oort Cloud's population. The current cloud is significantly less massive than the original cloud that formed early in the solar system's history. Understanding the rate of this depletion and how it has varied over time as the galactic environment changed is part of building a complete picture of the cloud's history. Conversely, the Oort Cloud may also be gaining some material from the interstellar medium through a process called capture. When an interstellar object like 2I/Borisov passes through the solar system, there is a small probability that it could be captured into a bound orbit by gravitational interactions with the Sun or the planets. This probability is very small for any individual interstellar object, since the relative velocities involved are typically too large for gravitational capture to occur efficiently. But over billions of years, and many interstellar objects passing through, some small amount of material may have been captured. The amount of captured interstellar material in the Oort Cloud is expected to be a small fraction of its total mass, and distinguishing captured objects from native Oort Cloud members based on their current orbital properties or compositions is extremely difficult. However, if a captured interstellar object were to eventually be sent as a long-period comet toward the inner solar system, detailed compositional analysis, similar to that applied to 2I/Borisov, might potentially reveal its exotic origin. The question of what the Oort Cloud tells us about the solar system's place in the galaxy is also philosophically interesting. The cloud extends from a few thousand to 100,000 astronomical units from the Sun, and its outermost edge is approximately 1.5 light-years away. The Milky Way galaxy is roughly 100,000 light-years in diameter. Our solar system orbits the galactic center at a distance of about 26,000 light-years, completing one orbit in roughly 225 million years. On the scale of the galaxy, even the Oort Cloud is tiny. The distance from the Sun to the outer edge of the Oort Cloud is 1.5 light-years, while the average distance between stars in our region of the galaxy is roughly 4 to 5 light-years. The Oort Cloud extends about 1/3 of the way to our nearest stellar neighbor, but only about 1.5 millionths of the way to the galactic center. It is, by any galactic measure, an extremely local structure. And yet, This local structure connects us to galactic dynamics in profound ways. The galactic tide that acts on the Oort Cloud is generated by the distributed mass of hundreds of billions of stars, gas clouds, and dark matter throughout the Milky Way. Perturbations from passing stars reflect the local stellar density and the dynamics of stellar motion in our region of the galaxy. The molecular cloud encounters that have shaped the Oort Cloud over its history are themselves the sites of ongoing star formation, connecting our solar system's history to the broader cycle of stellar birth and death in the galaxy. Understanding the Oort Cloud, therefore, requires understanding the solar system not as an isolated entity, but as a participant in the large-scale dynamics of the Milky Way. It is a reminder that our solar system is embedded in a galactic environment that has shaped it in significant ways over its long history, and will continue to do so in the future. The role of comets in the history of science, culture, and life on Earth provides an additional dimension to the significance of the Oort Cloud. Long before Oort proposed the cloud's existence, comets had fascinated and sometimes terrified human observers across cultures and centuries. In ancient and medieval cultures, comets were typically regarded as omens, usually of bad things to come. Their sudden and unpredictable appearances in the sky, combined with their dramatic visual character, made them seem like extraordinary events that must carry extraordinary significance. Comets were associated with the deaths of rulers, the outcomes of battles, and other significant historical events. The appearance of Halley's Comet in 1066, just before the Norman conquest of England, is depicted in the Bayeux Tapestry, and was interpreted at the time as an omen of the dramatic events that followed. The scientific understanding of comets developed gradually over the centuries. Aristotle had classified comets as atmospheric phenomena, occurring within Earth's atmosphere rather than in the heavens beyond. This view was challenged in 1577 when the Danish astronomer Tycho Brahe measured the parallax of a bright comet and determined that it was much farther away than the Moon, placing it definitively in the celestial realm beyond Earth's atmosphere. Edmund Halley's calculation in 1705 that the comets observed in 1682, 1607, and 1531 were all the same object. Returning to the inner solar system on a regular orbit was a landmark achievement. It demonstrated that comets followed predictable physical laws like other celestial bodies, and it made the prediction, confirmed after Halley's death, that the comet would return again in 1758. This was one of the early triumphs of Newtonian mechanics applied to celestial objects. The physical nature of comets was clarified progressively over the 19th and 20th centuries. The idea that comets are essentially dirty snowballs, solid bodies made of ice and dust that release gas and dust when heated by the sun, was proposed by Fred Whipple in 1950, the same year Oort published his cloud paper. Whipple's model explained many observed properties of comets, including the asymmetry between their behavior approaching and receding from the sun, and it has been largely confirmed by subsequent spacecraft missions to comets. The Giotto spacecraft, launched by the European Space Agency in 1985, flew past Halley's Comet in March 1986 and provided the first close-up images and measurements of a cometary nucleus. The nucleus was found to be an elongated, potato-shaped body, roughly 15 kilometers long and 8 kilometers wide, darker than coal in color due to a layer of complex organic material on its surface. The spacecraft detected water vapor as the dominant outgassing species, along with carbon dioxide, carbon monoxide, and various organic compounds. More recently, the European Space Agency's Rosetta mission spent over 2 years in orbit around comet 67P/Churyumov-Gerasimenko, a short-period comet from the Kuiper Belt, from 2014 to 2016. The Philae lander made the first soft landing on a cometary nucleus in November 2014. The data from Rosetta and Philae revealed an extraordinarily complex world, with a nucleus shaped like a rubber duck, formed from 2 separate lobes that gently collided and merged at some point in its history. The surface was covered with a diversity of terrains, from smooth plains of fine-grained material to rugged cliffs and exposed rock. Most importantly, for understanding comet composition and its implications for Earth's history, Rosetta's instruments analyzed the water vapor and other volatiles being released from the comet in unprecedented detail. The deuterium to hydrogen ratio in the comet's water was found to be significantly different from that of Earth's oceans, suggesting that comets from the Kuiper Belt like this one were not the primary source of Earth's water. This result does not rule out a contribution from long-period comets originating in the Oort Cloud, since Oort Cloud comets would have formed in different regions of the early solar system, and might have different isotopic signatures. The question of the origin of Earth's water is one of the more actively studied topics in planetary science, and it connects directly to the Oort Cloud question. If Earth's water, or a significant fraction of it, was delivered by long-period comets from the Oort Cloud, then the composition of the Oort Cloud has relevance not just for understanding the solar system's outer frontier, but for understanding the conditions that made life on Earth possible. The delivery of organic molecules by comets is an even more speculative but tantalizing topic. The chemistry of cometary nuclei is rich with the building blocks of biological molecules. Amino acids have been detected in cometary material and in meteorites thought to have cometary origins. Glycine, the simplest amino acid, was detected in samples returned from Comet Wild 2 by the Stardust spacecraft in 2006. Formaldehyde, hydrogen cyanide, and many other molecules relevant to prebiotic chemistry have been detected in cometary spectra. Whether these molecules could have been delivered to early Earth in biologically significant quantities, and whether they might have contributed to the emergence of life, is an open question. The conditions under which cometary impacts occurred on early Earth were violent, and it is not obvious that fragile organic molecules would survive the impact unaltered. However, some theoretical models suggest that a fraction of the organic material in an impacting comet could survive and be incorporated into the planet's surface chemistry under some impact conditions. The Oort Cloud is relevant to this discussion because it is the source of long-period comets, and long-period comets are more likely than short-period comets to have formed in the coldest, most volatile-rich outer regions of the early solar system. If organic molecules were particularly abundant in the outer solar system during planetary formation, Oort Cloud objects and the long-period comets derived from them might be especially rich sources of such material. This is one reason that astronomers and astrobiologists are interested in detailed compositional analysis of long-period comets. Each new long-period comet that swings through the inner solar system is an opportunity to sample the chemistry of the Oort Cloud and to test hypotheses about the role that cometary material might have played in seeding early Earth with the ingredients of life. The intersection between comet science and astrobiology illustrates the broader significance of understanding the Oort Cloud. The cloud is not just an astronomical curiosity or a boundary marker for the solar system. It is connected, through the mechanics of cometary delivery, to questions about the conditions for life, the history of Earth's surface chemistry, and the habitability of other worlds throughout the galaxy. If Oort clouds are common around stars with planetary systems, and if long-period comets derived from these clouds are a common mechanism for delivering volatile and organic material to inner planets, then the Oort cloud phenomenon might be a significant factor in determining which planetary systems develop conditions favorable for life. Systems with larger or more dynamically active Oort clouds might deliver more cometary material to their inner planets. Systems where the Oort cloud is efficiently depleted early in the system's history might deliver less. The details of how Oort clouds form and evolve could therefore have implications for the frequency of habitable worlds throughout the galaxy. The search for life beyond Earth and the broader understanding of where life might arise in the cosmos therefore has an unexpected connection to the study of icy objects at the frigid edges of solar systems. The humble comets that occasionally grace our night skies with their glowing tails are messengers not just from the outer solar system, but from the early history of the solar system's chemistry. And the Oort cloud from which they came is a repository of that ancient chemistry, preserved in the deep cold for billions of years, waiting to be understood. The scientific journey toward understanding the Oort cloud is in many ways characteristic of the broader enterprise of modern science. It begins with patient observation, the careful recording of where comets appear and how they move. It moves to pattern recognition, the discovery of statistical regularities in observational data. It produces theoretical proposals, the hypothesis of a vast cloud of icy objects at specific distances. It generates further tests and refinements, decades of computer simulations and additional comet measurements, and it connects to broader questions: the history of the solar system, the dynamics of the galaxy, the conditions for life, and the general problem of planetary system formation and evolution throughout the universe. No single step in this process is definitive on its own. Oort's original paper was not proof of the cloud's existence. The first computer simulations that produced Oort cloud-like distributions were not proof. The growing catalog of long-period comet orbits that fits Oort cloud predictions is not proof. But together, these many lines of evidence weave a net of inference that closes in on the reality of the cloud with increasing confidence over time. This is how science often works at its frontiers. not with a single dramatic revelation, but with a steady accumulation of consistent evidence from many different directions. The Oort Cloud has never been photographed, and may never be photographed by any technology in the foreseeable future. But it is as real as any other feature of the solar system that we know. It is a structure inferred from evidence, as surely as atoms were inferred from chemistry before electron microscopes could image them, as surely as black holes were inferred from stellar dynamics before gravitational wave detectors and event horizon imagers could confirm them directly. When the next long-period comet sweeps through the inner solar system, and astronomers train their telescopes on its glowing head and streaming tails, they will be observing a fragment of the Oort Cloud that has been dormant at the solar system's edge since before the dinosaurs walked the Earth. They will be sampling the chemistry of the primordial solar system, preserved in ice for billions of years. And they will be adding one more data point to the centuries-long project of understanding our place in the cosmos, the structure of our solar system from its innermost rocky worlds to its outermost frozen frontier. The Oort Cloud waits at that frontier, vast and silent and cold, indifferent to our attempts to understand it, but yielding its secrets gradually and patiently to the questions of the curious. One of the more fascinating aspects of Oort Cloud science involves the connection between the cloud and the processes by which the solar system first formed. The story of the solar system's origin is one of the great narratives of planetary science, and the Oort Cloud is both a product of that origin and a preserved record of its conditions. The solar system began approximately 4.5 billion years ago as a slowly rotating cloud of gas and dust, a fragment of a larger molecular cloud in our region of the Milky Way. This protosolar nebula, as it is called, was far larger than the current solar system, extending for thousands of astronomical units in its most diffuse outer regions. The cloud collapsed under its own gravity, spinning faster as it shrank due to the conservation of angular momentum, much like a figure skater spinning faster when pulling in their arms. As the cloud collapsed, most of its mass concentrated at the center, forming a dense protostar. The surrounding material flattened into a rotating disk, the protoplanetary disk, or proplyde, from which the planets eventually formed. The formation of planets from this disk is called planetary accretion. Dust grains stuck together to form pebbles. Pebbles clumped into boulders. Boulders accumulated into planetesimals, and planetesimals collided and merged to form the planetary embryos that eventually grew into the full planets over millions of years. The outer solar system, beyond the snowline, the distance from the protosun at which water ice could condense, was particularly rich in solid material. Ice could exist as a solid at these distances, greatly increasing the amount of condensable material available for planetary accretion. This is why the outer planets, Jupiter, Saturn, Uranus, and Neptune, are much more massive than the inner terrestrial planets. They formed in a region where material was both more abundant and, in the case of the gas giants, where the protoplanetary disk was still dense enough with gas to be accreted rapidly onto the growing solid cores. But not all the material in the outer solar system ended up in the planets. Enormous quantities of planetesimals were left over, occupying the spaces between the planetary orbits and beyond. As the planets grew and their gravitational influence strengthened, they began clearing the material around them. Some nearby planetesimals were accreted by the growing planets. Others were flung to more distant orbits. A significant fraction of planetesimals in the vicinity of the giant planets were thrown into highly eccentric orbits or ejected from the solar system entirely by close encounters with the massive growing planets. It is during this period of dynamical clearing that the Oort Cloud is believed to have been populated. Planetesimals, scattered from the giant planet region to very large distances, could have their orbits further modified by galactic tidal forces and perturbations from nearby stars in the solar birth cluster. These secondary perturbations raise the perihelion distances of the scattered planetesimals, the closest approach points of their orbits to the Sun, to such large values that the planets could no longer significantly perturb them. The planetesimals became effectively detached from the planetary system and entered the large, roughly circular orbits that characterize the Oort Cloud. The efficiency of this process depends critically on the dynamical history of the giant planets. If Jupiter and Saturn migrated significantly during the first few 100 million years of the solar system's history, their migration would have scattered large quantities of material from the outer solar system. The leading models of giant planet formation, including the NICE model and its successors, predict that substantial migration did occur, and that this migration was indeed a major driver of the initial population of the Oort Cloud. The timing of Oort Cloud formation, relative to the dispersal of the solar birth cluster, is also important. The cluster dispersed over several hundred million years after the Sun formed. During this period, the neighboring stars in the cluster were much closer to the Sun than they are today, and their gravitational influence on the outer solar system was correspondingly stronger. Material scattered to large distances by the giant planets during this period would have been much more efficiently captured into stable Oort Cloud orbits because the neighboring stars helped circularize their orbits. Material scattered after the cluster dispersed would have been less efficiently captured, since, without neighboring stars to circularize the orbits, many scattered objects would eventually have been lost from the solar system entirely. This timing argument suggests that most of the Oort Cloud's population was established during the first several hundred million years of the solar system's history, when the birth cluster was still intact. The cloud, as it exists today, is essentially a fossil of that early formation epoch, a record of the conditions in the outer protoplanetary disk and the dynamical processes that redistributed material to extreme distances. The composition of the Oort Cloud therefore reflects the composition of the outer protoplanetary disk 4.5 billion years ago. This was a region dominated by water ice, carbon dioxide, carbon monoxide, methane, and other volatile compounds, along with silicate dust and various complex organic molecules. These compounds formed at temperatures far below 0 degrees Celsius in the cold outer reaches of the protoplanetary disk, where they had been synthesized from simpler elements in the interstellar medium before the solar system even formed. The interstellar heritage of cometary material is well established. Analysis of isotopic ratios in cometary material, particularly the ratios of different isotopes of hydrogen, carbon, nitrogen, and oxygen, shows signatures that are characteristic of material processed in the cold interstellar medium rather than in the warmer inner solar system. The complex organic molecules found in comets include many compounds that have also been detected by radio telescopes in interstellar molecular clouds, the same types of clouds from which star and planetary systems form. This connection between cometary chemistry and interstellar chemistry suggests that the building blocks for the chemistry of life are widespread in the galaxy. The same molecular ingredients found in comets are also found in star-forming regions throughout the Milky Way and in other galaxies. When new planetary systems form, they inherit this chemical legacy from the interstellar medium. The comets and their Oort clouds carry this interstellar chemistry in frozen form, and when those comets are eventually sent toward inner planets, they deliver some of this interstellar chemical heritage to those planets. The implications of this are potentially profound. If the ingredients for life are widespread in the galaxy, if they are routinely delivered to inner planets by comets from Oort-like clouds, then the emergence of life might not be an extraordinarily improbable event, dependent on a unique set of circumstances on a single planet. Rather, life's emergence might be facilitated by chemistry that is assembled in interstellar space, delivered to many planetary systems, and given the opportunity to develop wherever conditions are suitable. This is speculative, of course. The gap between having the chemical ingredients of life and actually having life is enormous and poorly understood. The emergence of life on Earth required not just the right chemistry, but also the right physical conditions. Liquid water, a stable energy source, protection from destructive radiation, and presumably much more that we do not yet understand. But the widespread distribution of the relevant chemistry throughout the galaxy, mediated in part by cometary delivery from Oort-like clouds, is a real observation rather than speculation. The Oort cloud is therefore connected to one of the deepest questions in science. Is life common or rare in the universe? It does not answer that question, but it contributes one piece of the puzzle. It is a mechanism by which ancient interstellar chemistry can be preserved and delivered to newly habitable planetary environments. It is a bridge between the chemistry of star-forming regions and the chemistry of planetary surfaces. And it is a reminder that the solar system, and indeed all planetary systems, exist within a galactic context that shapes them in ways that are still being understood. Science at its best is characterized by the discovery of unexpected connections between apparently unrelated phenomena. The connection between the dynamics of the outer solar system and the potential for life on Earth is one such unexpected connection. When Oort proposed the existence of his cloud in 1950, the idea that long-period comets might be relevant to the origin of life was probably not a primary concern. The theory was motivated by purely astronomical questions about the origin and dynamics of comets. But science rarely stays within the boundaries that motivated a particular investigation. The Oort cloud has proven to be relevant to questions in planetary science, galactic dynamics, stellar formation, the history of life on Earth, and the search for life elsewhere in the universe. It is a small part of the cosmic picture, but a part with ramifications that extend in many unexpected directions. As our observational and computational capabilities continue to improve, the understanding of the Oort cloud will deepen. More long-period comets will be discovered and characterized. More stellar encounter histories will be reconstructed using precise astrometry from future Gaia data releases. More sophisticated simulations of solar system formation will refine our understanding of how the cloud formed and how its properties have changed over time. The Vera C. Rubin Observatory will expand the census of small solar system bodies in the transitional region between the Kuiper Belt and the inner Oort cloud, and the James Webb Space Telescope and its successors will continue to reveal the chemistry of comets in unprecedented detail. Each of these advances will add resolution to the picture of the Oort cloud, filling in details that are currently blurry or missing entirely. The process is slow and incremental by its nature. There will be no single dramatic moment when the Oort cloud is finally confirmed or its properties finally determined with certainty. Instead, confidence and knowledge will grow steadily, as they always do in science, through the accumulation of consistent evidence from many different directions. The Oort cloud will likely remain one of the few major features of our solar system that has never been directly observed within any individual human lifetime. Its scale and distance make direct observation with foreseeable technology essentially impossible. But indirect knowledge can be deep and reliable. We know that the Earth orbits the Sun not because we have ever stood in space and watched it happen, but because the evidence for it is overwhelming and consistent from many independent lines of observation and measurement. The Oort cloud is known in the same way, through evidence that is indirect but deep and consistent. It is a real structure, populated by real objects, exerting real gravitational effects, and sending real comets toward the inner solar system. That it has never been photographed does not diminish its reality in any scientific sense. It is part of the solar system, part of our neighborhood in the cosmos, part of the ancient history that shaped the world we live on. And as our capabilities grow, as our telescopes become more sensitive, our simulations more sophisticated, and our understanding of comet chemistry more detailed, the Oort cloud will yield its remaining secrets gradually and patiently. The frozen fragments of the early solar system that drift in silence at its far edge, 4.5 billion years old and counting, will continue to send their ambassadors sunward from time to time, glowing briefly as they pass the sun before retreating once more into the cold darkness beyond the edge of the known solar system. There remains one more dimension of the Oort cloud story worth exploring in depth. The question of what it means for our understanding of the solar system to have such a vast, unobserved structure defining its outermost boundary. Throughout the history of astronomy, the perceived boundaries of the solar system have shifted as new discoveries push those boundaries outward. In ancient times, the solar system was understood to extend only as far as Saturn, the most distant planet visible to the naked eye. The discovery of Uranus in the 18th century extended the solar system's known boundary to roughly 19 astronomical units. Neptune's discovery in the 19th century pushed it to 30 astronomical units. Pluto's discovery in 1930 briefly suggested a boundary at about 39 astronomical units, though Pluto's true nature as a Kuiper Belt object was only recognized decades later. The discovery and characterization of the Kuiper Belt in the 1990s fundamentally changed the picture of the outer solar system. It revealed that the region beyond Neptune was populated by thousands of objects, not just Pluto, and that the solar system's structure extended much farther than had been recognized. The scattered disk and the growing catalog of distant trans-Neptunian objects further expanded the recognized extent of the solar system to distances of hundreds and eventually thousands of astronomical units. The Oort cloud, if it exists as theorized, extends this boundary to 100,000 astronomical units, a scale so much larger than the planetary system that it almost defies intuition. In a sense, the planetary system, everything from Mercury to Neptune with all its accompanying belts and debris, occupies only a tiny fraction of the total volume of the solar system, as defined by the Oort cloud. If you think of the solar system as a sphere extending to the outer edge of the Oort cloud, the planetary zone inside Neptune's orbit occupies only about 0.01% of that total volume. This perspective inverts the usual way of thinking about the solar system. We typically focus on the planetary zone because it is most accessible, most studied, and most relevant to our direct experience. But by volume, the solar system is almost entirely Oort cloud. The planets, the inner solar system, Everything we typically mean when we talk about the solar system is just a tiny, dense knot at the center of an enormous, sparse, and largely invisible sphere of ancient ice. The Oort Cloud also challenges our intuition about what it means for something to be part of the solar system. Objects in the Oort Cloud are gravitationally bound to the Sun, orbiting it on enormously elongated paths that take millions of years to complete. But at their farthest points from the Sun, they are 1.5 light years away, deep in what would normally be called interstellar space. The boundary between the solar system and interstellar space is not a sharp line. It is a gradual transition zone that extends from the heliopause at about 120 astronomical units, where the solar wind gives way to the interstellar medium, through the Kuiper Belt and scattered disk, to the inner Oort Cloud, and finally to the outer Oort Cloud's edge, where objects barely remain gravitationally captured by the sunday. The concept of the solar system as a sharply bounded entity turns out to be a simplification. The real situation is a continuum of decreasing solar influence with increasing distance from the intense environment of the inner solar system, through the increasingly cold and dark outer regions, to the barely gravitationally bound outer Oort Cloud. The solar system does not end so much as it fades, becoming indistinguishable from interstellar space at distances where the sun's gravity and light and particle emissions have become negligibly faint. This gradual transition has practical implications for interstellar travel. The concept of leaving the solar system and entering interstellar space sounds like a sharp boundary crossing, but the reality is more nuanced. Voyager 1 became the first human-made object to cross the heliopause and enter what NASA calls interstellar space. But it is still within the gravitational sphere of influence of the Sun, still technically bound to the Sun gravitationally, still surrounded by Oort Cloud material at its present distance of about 237 astronomical units from the sunday. It will remain within the Oort Cloud for tens of thousands of years. In a meaningful sense, it has not yet left the solar system. A spacecraft that truly left the solar system would need to reach distances beyond the Oort Cloud's outer edge, perhaps beyond 150,000 astronomical units, where the Sun's gravity can no longer maintain a bound orbit. No human-made spacecraft is anywhere near achieving this on any foreseeable timescale with current technology. The Oort Cloud, therefore, also serves as a reminder of the gulf between our current technological capabilities and true interstellar travel. The nearest star system is 4 light-years away. Our fastest spacecraft would take tens of thousands of years to reach it. The Oort Cloud, at 1.5 light-years distance, would take 30,000 years to traverse at current spacecraft speeds. The very first step of any genuinely interstellar journey, crossing the Oort Cloud's outer boundary, is already an undertaking that exceeds the span of recorded human history by an order of magnitude. This is not cause for despair, but for perspective. The universe is vast beyond easy comprehension. The solar system, including its invisible Oort Cloud boundary, is vast beyond the reach of our current technology. Understanding the scale of the challenge is prerequisite to any realistic thinking about meeting it. Future generations may develop propulsion technologies that make these journeys feasible. Nuclear propulsion, antimatter drives, laser sail systems, and other concepts under theoretical development could potentially reduce travel times dramatically. But these remain in the realm of engineering challenges, some fundamental and some merely practical, that have not yet been met. In the meantime, the study of the Oort Cloud proceeds through the methods available: mathematical inference, numerical simulation, and the patient analysis of cometary messengers. It is work that advances slowly but steadily. The picture of the outer solar system that astronomers hold today is dramatically more detailed and nuanced than the picture available to Oort in 1950. And the picture available in another 70 years will doubtless be dramatically more detailed still. Science makes progress even when direct observation is impossible. The Oort Cloud's history as a scientific idea demonstrates this clearly. From a theoretical proposal based on a few dozen comet orbits to a well-supported hypothesis backed by decades of simulation, observation, and inference, the cloud has become an integral part of our understanding of the solar system and our place in the galaxy. Its basic existence is as well established as any unobserved feature of the physical world can be. What remains to be determined are the details: the exact extent of the cloud, its precise population, its compositional diversity, its dynamical history, and its future evolution. These are questions that will keep planetary scientists dynamicists, and comet observers occupied for generations to come. They are questions worth asking, not just for academic completeness, but because the answers connect to the broader story of how planetary systems form and evolve, and how the conditions for life arise in the cosmos. The Oort Cloud is, in every sense, a frontier. A physical frontier at the edge of the solar system, where solid ground gives way to frozen darkness and the sun's light fades to a barely perceptible star. An intellectual frontier where confident knowledge transitions to careful inference. And a technological frontier that marks the current limit of human reach into the cosmos. Frontiers have always driven scientific inquiry. The desire to understand what lies beyond the known, to push the boundaries of knowledge into territory that has never been mapped, is one of the fundamental impulses of science. The Oort Cloud is a frontier of exactly this kind, enormous and invisible and full of secrets, waiting patiently at the edge of the world we know. The next time a long-period comet appears in the night sky, whether visible to the naked eye or requiring a telescope to find, it is worth pausing to consider its origin. That small glowing spot of light, trailing its gossamer tail of sublimating ice and liberated dust, has spent billions of years in the cold, dark quiet of the Oort Cloud, orbiting the sun in a vast, slow arc at distances that stagger the imagination. Something disturbed its orbit, a passing star's gravity, a galactic tidal nudge, or some complex interaction in the outer reaches of the solar system, and sent it on its long falling journey inward. That journey may have taken millions of years. The comet has traveled further than any human spacecraft, from a realm we have never reached and may never reach, to pass briefly through our neighborhood and give us a chance to study the ancient frozen record it carries. In that sense, every long-period comet is a gift from the Oort Cloud, a sample delivered to our doorstep by the mechanics of orbital dynamics. And every observation of that comet, every spectrum taken, every orbit calculated, every chemical abundance measured, is a small contribution to our understanding of the cloud that sent it, and of the ancient solar system that created the cloud 4.5 billion years ago. The Oort Cloud remains one of astronomy's most compelling unknowns, not because it is necessarily mysterious in a supernatural sense, but because it is genuinely not yet fully understood despite being our nearest cosmic frontier. The scientific tools to understand it better exist, or are being developed. The will to use them is evident in the ongoing work of hundreds of astronomers worldwide, and the patience to do the science properly, accumulating data over years and decades, refining models iteratively, and building knowledge through the slow accretion of consistent evidence, is the defining characteristic of the scientific enterprise itself. There is every reason to expect that the next several decades will bring significant advances in our understanding of the Oort Cloud. New survey telescopes will discover thousands of new comets. New simulations will refine our models of the cloud's formation and evolution. New missions to the outer solar system may probe the transitional regions between the Kuiper Belt and the inner Oort Cloud. And new detections of interstellar objects, like 2I/Borisov, will continue to provide comparison points from Oort-like clouds around other stars. The Oort Cloud, invisible and ancient, extending 1.5 light years in every direction around our sun, is there. The evidence says so. The mathematics says so. The comets that arrive from its depths say so. And as science continues its patient work of inquiry and inference, the cloud will continue to yield its secrets, one by one, to those who ask the right questions and look carefully at the answers the universe provides.